Improvement of engineering properties of subgrade soil with locust bean waste ash and quarry dust. Abstract: the experimental program was designed to study the effect of locust bean waste ash admixed with quarry dust on the index and strength properties of lateritic soil. The percentage mixtures of QD/LBWA were 0, 2, 4, 6, and 8% by dry weights of the soil, respectively. The soil sample used for was obtained along Ajase-Ipo interchange of Ilorin-Offa and Ilorin-Oro Road, Kwara State, Nigeria. The preliminary investigations conducted on the soil sample indicate that the soil is highly plastic with about 71% of the soil particles passing the BS. Number 200 sieve. The plasticity index values for all the concentration of the additive exceeded the 30% value prescribed for subgrade materials by the Nigeria General Specification, 1997. The peak MDD values recorded for BSL, was and BSH compactive efforts are respectively 1.50, 1.68, and 1.72 mg/m3 at 6% OPC/6% LBWA treatment. The OMC, on the other hand, decreased with higher compactive efforts but increased with higher LBWA contents. The unconfined compressive strength, UCS, values for natural soil compacted with BSL, was and BSH energies at 7 days curing period are 47, 390 and 750 kN/m2 respectively and increased to 586, 1125 and 1240 kN/m2 at 6% QD/6% LBWA treatment. In conclusion, the optimum blend of 6% QD/6% LBWA treatment on the lateritic is to be used as sub-base material when compacted with the British Standard Heavy Energy. Keywords: curing, laterity soil, locust bean waste ash, quarry dust, subgrade. Introduction. To the civil engineer, soil is any uncemented accumulation of mineral particles formed by weathering of rocks. Soils are generally used as foundation or as construction materials. A class of soil, known as expansive soils, when used as foundation material, is usually affected by environmental conditions and they undergo detrimental volumetric and hydraulic conductivity changes because of the variation in moisture contents. Expansive soils are, therefore, soils with potential for shrinking or swelling under changing moisture condition 1. These soils cause more damage to structures, particularly light building and pavements, than any other natural hazards, including earthquakes and floods too. The subgrade soil is the underlying soil on any ground surface and it must be able to support loads transmitted from pavement structure without excessive deformation under adverse climatic and traffic conditions. It is an established fact that not all soils possess the desirable qualities for use as pavement material. Additionally, a site where groundwater table is high, the strength of such subgrade is also adversely affected by moisture infiltration due to capillary action. When such soils cannot be replaced, their subgrade performance could be improved by several modification techniques 3, 4, 5, 6. Deficient soils are soils with potential for shrinking or swelling under changing moisture condition 1. They contain more of montmorillonite with subsequent manifestation of swell properties and expansive tendencies 7. They are poor and undesirable for engineering purposes but their properties could be improved by modification/stabilization processes to reduce the swell-shrink tendencies of the soil and also makes the soil less plastic. 7, 8, 5, 9. Pozzolanas are silicious and aluminous industrial or agricultural waste materials that possess little cementitious value but, will, in the presence of moisture chemically react with calcium hydroxide at ordinary temperature to form compounds possessing cementitious properties. Recent studies 10, 5, 11, 12, 9, 13, 14, 16, 17, 18, 19, have focused on the use of these materials in the improvement of deficient soils. Additionally, the use quarry dust dates back the beginning of the century and in a recent research by 20, it was observed that the use of quarry dust increased the dry density of a deficient soil by 20% and decreased the moisture content by 15%. Materials and methods. Materials. Lateritic soil. The soil sample used for the research was obtained along Ajase-Ipo interchange of Ilorin-Offa and Ilorin-Oro Road, Kwara State, Nigeria. The topsoil was removed to a depth of 0.5 before the soil samples were taken. They were sealed in plastic bags to avoid loss of moisture and taken to the laboratory. The soil samples were air-dried before pulverizing to obtain particles passing sieve 4.75 mm. Quarry dust. The quarry dust used for the work was obtained from Bora Garden along Offa Ajase Road close to Green Park, Ajase-Ipo, Kwara State. The materials were kept properly in a closed container and air-dried before passing through sieve no 4.75 mm. Locust bean waste ash. The locust bean waste ash, LBWA, used was obtained locally from burning the husks sourced from Igbara village along Offa Ajase Road, Offa, Kwara State. The dried husks were completely burned at a temperature of 1000 C with Merfel furnace at Science Laboratory Technology, SLT, Department, Federal Polytechnic, Offa. The ash was passed through sieve no 850 before it was admixed in the appropriate percentages. Conducted in accordance with Test 121. Part 2 for the natural soil and 23 for the stabilized soils. 7. Compaction characteristics. Maximum dry density. The compaction tests were carried out for the natural soil and the stabilized soils, in different percentages, all according to 21, using the British Standard Light, West African Standard and the British Standard Heavy, in accordance with the Nigerian General Specification, 1997. The bulk density in MGL-M3 was later calculated for each compacted layers using methods. M2-M1. The experimental program was designed to study the effect of locust bean waste ash admixed with quarry dust on the index and strength properties of lateritic soil. The percentage mixtures of QD/LBWA were 0, 2, 4, 6, and 8% by dry weights of the soil, respectively. Natural moisture content. The natural moisture content of the soil as obtained from the site was determined in accordance with 21. The natural moisture content, as collected from the site, is calculated as the average as given by EQ, 3.1. Durability assessment. Resistance to loss in strength. The durability assessment, under adverse field conditions, of the soil sample was determined by resistance to loss in strength when immersed in water. It was expressed as the ratio of UCS of the specimen cured for 7 days and soaked for another 7 days to the UCS of the specimen cured for 14 days. 7. Proposed 80% resistance to loss in strength for the ratio of the UCS of a specimen cured for 7 days and soaked for 4 days to the UCS of the specimen cured for 14 days. High moisture content of 15%. The index properties are summarized in Table 1, while its oxide compositions are summarized in Table 2. The soil belongs to the CH group in the Unified Soil Classification System 24, soil group of the Ashto Soil Classification System 25. The soil is reddish-brown in color, from wet to dry states, with a liquid limit of 43.9%, plastic limit of 29.0% and plasticity index of 21.9%. The soil has a free swell of about 55%, soak CBR values of 5%, 6%, and 9% for the 3 energy levels of British Standard Light, West African Standard and the British Standard Heavy, respectively, and UCS values of 251, 364 and 687 kN/M2 for the energy levels, respectively. The soil was found to be highly plastic and falls below the standard recommendation for most geotechnical construction works, especially for sub-base or base courses in highway construction 26, 27. The little amount of calcium in LBWA, 1.08%, to be used for the stabilization process was supplemented by the calcium present in a typical of OPC, of 63%. The higher silicon and aluminium oxides in LBWA, also aided by the coarse nature of the quarry dust, will provide the required reaction needed for stabilization. Atterberg limits plasticity index. The variation of the plasticity index of soil cement mixtures with LBWA contents are shown in Fig. 2. The reduction in plastic limit and increase in liquid limit were accompanied by a general increase in the plasticity index value from a value of 22.9% to a peak value of 48.6% at 4% QD/6% LBWA treatment. Aiken-Maid, 2008, reported the same trend of increasing LL, pi, and decreasing PL with increasing admixture contents on stabilizing black cotton soil with LBWA. The same trend was also reported by Stephen, 2005, when he researched into the effect of bagasse ash on the stabilization of the soil. Optimum moisture content. The variation of optimum moisture content of soil cement mixtures with LBWA contents for BSL, WAS and BSH compactive efforts are shown in Figs 6, 7, and 8 respectively. It is observed that the OMC values when compaction was at the three energy levels increased to peak values at 6% LBWA for all cement contents for all the compactive efforts. The WAS compaction MDD decreased to a value of 1.5 mg/m3 at 2% QD/8% LBWA, and that may not be unconnected with the presence of large low-density aggregate of LBWA particles replacing the soil with a higher specific gravity. The variation of MDD for the British Standard Heavy, BSH, compaction is also in conformity with the other two energy efforts. Its MDD increased from a minimum 1.63 mg/m3 in the natural state to a maximum 1.72 mg/m3 at 6% QD/6% LBWA. The trend of increasing MDD with admixture contents was reported by 9 and to the same peak value of 6% for OPC before it experienced reduction in the values at higher admixture contents. 28. The OMC for BSL compaction increased from 34% for the natural state to 40% at 8% QD/6% LBWA. Further addition of LBWA, to 8%, led to a decrease in the OMC to a value of 26% at 0% QD/8% LBWA. In the case of the WAS compaction, the OMC increased from 28% for the natural state to a maximum value of 38% at 8% QD/6% LBWA, which later decreased to 26% at 2% QD/8% LBWA. For the BSH compaction, a similar trend was also noticed, whereby the OMC increased from its natural state of 22% to 33% at 6% QD/6% LBWA. Research works of 929, 31, 27, 28, 32 agree with the trend of increasing OMC with admixture contents. An explanation that was offered for these trends is that there was increasing desire for water which commensurates with the higher amount of the additives because more water was required for the dissociation of admixtures with Ca2+ and O ions to supply more Ca2+ for the cation exchange reaction. Another reason could be due to the increasing surface area caused by the higher amount of the additives, which required more water for the lubrication of the entire matrix. It was also observed that OMC decreased with higher compactive efforts because it was easier to break down flocculated aggregates, destroy shear planes and eliminate large pores, at higher compactive efforts. 9. Strength characteristics. Unconfined compressive strength. The general test recommended for use in the determination of the additive to be used in the stabilization of soil is the unconfirmed compressive strength, UCS, test 33. It is an important factor in the evaluation of the design criteria for the use of soil as a pavement material. 7. The variation of UCS of soil cement mixtures cured for 7 days with LBWA contents for BSL, WAS and BSH compactive efforts are shown in Fig. 9, 10, and 11 respectively. The UCS values for the BSL compaction showed a sharp increase from 47 kN/m2 for the natural soil to 586 kN/m2 at 6% QD/6% LBWA. Subsequent addition of LBWA content did not increase the UCS, rather, it recorded a slight decrease to a value of 323 kN/m2 at 6% Qd/8% LBWA because of insufficient water to take the pozzolanic reaction to completion. It falls under A7-6, 13, classification 425 and CH according to Unified Soil Classification System 24. The natural soil has high moisture content of 15%. It has liquid limit of 44%, plastic limit of 21%, plasticity index of 23%, linear shrinkage of 17%, free swell of 55%, specific gravity of 2.34 and Enbury classification of high swell potential. All these values indicate that the soil is highly plastic with about 71% of the soil particles passing the BS. Number 200 sieve. The strength characteristics are also very low, thereby rendering the soil unfit for sub-base or road-base courses. The plasticity index values for all the concentration of the additive exceeded the 30% value prescribed for subgrade materials by the Nigeria General Specification, 1997. In the variation of resistance to loss in strength of soil QD mixtures with LBWA contents for BSL, WAS and BSH respectively shown in Figs 12, 13, and 14, the resistance to loss in strength increased from 15, 27, and 35% for the natural soils compacted with BSL, WAS and BSH energies to peak values of 32, 43, and 61% at 6% QD/8% LBWA, 8% QD/0% LBWA and 6% QD/6% LBWA. Respectively. All the peak resistance to loss in strength values fell short of the acceptable 80%. 1V Conclusion and Recommendation. Conclusion. The preliminary investigation conducted on the lateritic soil collected at Ajase-Ipo, Kwara State shows that the unconfined compressive strength, UCS, values for natural soil compacted with BSL, WAS and BSH energies at 7 days curing period are 47, 390 and 750 kN/m2 respectively and increased to 586, 1125 and 1240 kN/m2 at 6% QD/6% LBWA treatment. The values of UCS for both BSL and WAS fell short of the requirement based on Road Note 31, TRRI, 1977, requirement for economic range of OPC stabilization. However, the UCS value of the BSH compaction could be acceptable for sub-base courses of pavements. The resistance to loss in strength of the soil increased from 15, 27, and 35% for the natural soil to peak values of 32, 43 and 61% for BSL, WAS and BSH energies at 6% OPC/8% LBWA, 8% OPC/0% LBWA and 6% OPC/6% LBWA, respectively. Only 61% resistance to loss in strength, 39% loss in strength, at 6% OPC/6% LBWA with BSH compaction is close to the limiting value of 80% resistance to loss in strength 7 based on 4 days soaking. The 6% OPC/6% LBWA treatment of the soil can be used, at BSH compaction, for sub-base material because the soil was subjected to a harsher condition, of 7 days soaking, and due to the time-dependent gain in strength advantage of the pozzolana. Recommendation. Based on the results obtained, the optimum blend of 6% QD/6% LBWA treatment on the lateritic is to be used as sub-base material when compacted with the British Standard Heavy Energy. V. Acknowledgement. The research was fully funded by the intervention of Tertiary Education Trust Fund, TET Fund, of the Federal Government of Nigeria, through the Institution-Based Research, IBR, at the Federal Polytechnic Yok, Offa, Kwara State, Nigeria.